Here, we're going to step back from individual protocols and named attacks and talk about the underlying reason quantum-secure systems fail in the real world without ever being broken. When people hear the phrase quantum secure, they usually interpret it as an absolute claim that the system cannot be compromised. But that's not what the term actually means. Quantum secure means secure under a specific set of assumptions: independent executions, memoryless components, static adversaries, and perfectly modeled behavior. Those assumptions are what make the proofs work. The problem is that real systems do not live inside proofs. Real systems run continuously, they carry state, they recalibrate hardware, and they respond consistently to repeated interaction. That gap between mathematical certainty and physical reality is where failure emerges. Attacks don't disable systems or shatter protocols. They infer behavior. They learn how thresholds are set, how calibration drifts, how hardware responds, and how information accumulates below detection limits. By the time something is detected, the relevant information has already been extracted. Nothing has been violated, nothing has been forced, and nothing looks abnormal. The system behaves exactly as designed, and that is precisely why the failure is so hard to see. In this video, we're not going to argue that the math is wrong or that quantum cryptography doesn't work. Instead, we're going to show why security depends on assumptions surviving implementation, and what happens when they don't. Here we need to be precise about language, because a lot of confusion comes from how the term quantum secure is used. Quantum secure does not mean invulnerable, and it does not mean immune to attack. It means secure under a specific model. The proofs assume that executions are statistically independent, that key material carries no history from one run to the next, that adversaries are static and finite, and that system behavior is perfectly captured by the mathematical model. Under those assumptions, the guarantees hold. But real systems violate every one of those conditions. They operate continuously, not in isolated trials. They carry implicit memory through hardware state, calibration drift, and accumulated interaction. They respond, adapt, and recalibrate in ways that are necessary for stability but invisible to the formal model. And over time, their behavior inevitably deviates from what the proof assumes, even if nothing appears to go wrong. This is not a flaw in the mathematics. It is a mismatch between what is proven and what is deployed. When people say a system is quantum secure, they are usually referring to the pyramid on the left. What actually runs in the real world looks like the list on the right. The gap between those two is not hypothetical. It is where learning happens, where information accumulates, and where security quietly erodes without ever being formally violated. Here we see how failure emerges without ever announcing itself. None of these mechanisms require a violation, a spike, or an alarm condition. They operate entirely inside normal behavior. Detectors respond consistently to repeated patterns, which means their outputs are not random in the way proofs assume. They are repeatable, and repeatability creates structure. Calibration begins with careful tuning, but over time it drifts as systems adapt to temperature, load, aging components, and environmental variation. That drift is not a bug. It is necessary for stability, but it quietly moves the system away from the idealized model. Threshold learning happens when adversarial interaction probes behavior just below detection limits, run after run, allowing responses to be inferred without ever crossing a line. And state leakage accumulates because each execution leaves behind a fragment of residual information, not enough to matter on its own, but enough to matter in aggregate. What ties all of this together is that nothing here looks wrong. Every response is expected. Every adjustment is within specification. Every run is valid. No threshold is crossed, and no alarm is triggered. Yet, over time, These perfectly normal behaviors compound into a clear picture of how the system works. Failure does not arrive as a moment. It arrives as an accumulation. Here the problem becomes clear. Failure is hard to detect precisely because nothing looks wrong. Outputs remain stable, consistent, and statistically well-behaved, so from the outside, the system appears healthy. Adjustments that matter most are legitimate ones: calibration, tuning, compensation. The same processes engineers rely on to keep systems running reliably. Those alterations don't resemble attacks, they resemble maintenance. At the same time, no formal security condition is violated. Thresholds are respected, error rates remain acceptable, and proofs continue to apply exactly as written. When auditors or automated checks look at the system, everything passes. That's because most verification processes are confirmatory, not exploratory. They ask whether known conditions are satisfied, not whether unknown structure has been learned. The result is a system that behaves normally while drifting away from the assumptions that originally justified its security guarantees. Nothing trips, nothing spikes, and nothing demands intervention. Yet, underneath that calm surface, information is accumulating and behavior is being inferred. The system hasn't failed in a dramatic way. It has failed quietly by remaining correct, compliant, and predictable long after the model stopped describing what was really happening. Here, the core failure mechanism comes into focus. Security doesn't collapse because the mathematics are wrong. It collapses because the guarantees remain tied to assumptions that no longer describe what is actually running. Proofs establish guarantees inside an abstract model, and those guarantees are real, but only as long as the underlying assumptions hold. Implementation lives in a different layer. Real systems carry state, adapt to operating conditions, recalibrate components, and respond to repeated interaction in ways the model does not capture. At the low level, the system behaves consistently and predictably, which is exactly what engineers want. At the high level, however, that same consistency creates a mismatch between what is assumed and what is occurring. Security continues to reason about idealized behavior, while reality accumulates structure through natural operation. Nothing dramatic breaks, nothing violates a rule, and nothing forces the system outside its defined boundaries. Instead, security quietly sticks to assumptions that are no longer grounded in the physical behavior of the system. The guarantees remain formally correct, but they apply to a version of the system that no longer exists. Failure emerges not as an event, but as a divergence between the world the proof describes and the world the implementation inhabits. Here we're looking at a very specific, very real mechanism that shows up in deployed quantum systems: Qubit loss. Loss is treated as noise, something to be filtered, compensated for, or discarded, and under normal operation, that's exactly what happens. Qubits are labeled, processed, and when one is lost, the system performs a legitimate adjustment. Filters engage, frequencies are recalibrated, and the remaining qubits are routed forward as if nothing meaningful occurred. From the system's perspective, this is correct behavior. Nothing is broken, and no security condition is violated. But loss is not neutral. When loss occurs repeatedly and asymmetrically, it begins to correlate with underlying state information. In the normal process, those correlations are invisible because the system averages them away. Under adversarial probing, however, loss becomes a signal. By controlling when and how probes occur, an observer can bias which qubits are more likely to be lost, and that bias propagates forward into the surviving state. Each individual event looks harmless. Each adjustment looks legitimate. But over many runs, the remaining qubit carries a measurable skew toward one outcome. No threshold is crossed, no alarm fires, and no failure is detected. Yet information has leaked. The key point is that loss does not have to reveal everything at once to matter. It only has to reveal a little, consistently. When loss interacts with adaptive probing, it stops being noise and starts becoming information, quietly reshaping the state distribution while the system continues to believe it is operating securely. Here we get to a subtle but critical point. Defenses themselves generate information. Every mechanism designed to protect a system has to make decisions, and decisions produce signals. Side channels are the most obvious example. Resource usage, timing, power, and response patterns all reflect internal state. But even higher-level defenses leak insight. Error-correcting codes don't just fix mistakes. The way errors are corrected, and which corrections succeed, reveals structure about what the system is experiencing internally. Flaw remediation introduces another signal. When patches are prioritized, deployed incrementally, or tuned over time, those choices expose which parts of the system matter most. And countermeasure adaptation creates feedback by definition. When a system changes behavior in response to perceived risk, it teaches an adversary which inputs trigger which defenses. None of this requires bypassing security or violating protocol rules. These signals exist because the system is alive, monitoring itself, correcting itself, and responding to its environment. From a defensive perspective, that feedback is necessary to stay operational. From an adversarial perspective, it is a learning channel. Every defense has a signal, and every signal can be observed, correlated, and tested. Over time, those signals stop being noise and start becoming a map of how the system protects itself, and where it can be influenced without ever being attacked in the traditional sense. Here, this same pattern shows up in a different domain, but the logic is identical. Data poisoning is hard to detect because it doesn't look like sabotage. It looks like normal data. The perturbations introduced are subtle, small enough to fall within expected variability, so statistically they blend in with natural noise. The sources appear realistic and relevant, drawn from the same distributions the system already trusts. During training, nothing diverges. Gradients converge. Loss decreases, and performance metrics improve exactly as expected. From the outside, the system looks healthy. What changes is not the visible behavior, but the internal decision boundaries. Small, carefully placed influences accumulate until they shape how the model responds under specific conditions. There is no dramatic failure point, no obvious corruption, and no single sample that can be flagged as malicious in isolation. Control is achieved quietly, through consistency and repetition, not disruption. The model behaves as designed, the statistics hold, and validation passes. Yet its behavior has been nudged in ways that only appear when the right inputs arrive. This is why poisoning works. The system is not broken, it is taught, and it learns exactly what it is shown. Here, this slide captures a timing asymmetry that shows up in almost every real defensive system: the cold start problem. Defenses don't begin with certainty. They begin in an uncertain state, with no reliable baseline to validate behavior against. Before any meaningful judgment can be made, the system has to observe, collect data, and sample patterns long enough to decide what normal looks like. That process takes time. During that window, policies are not yet tuned, thresholds are provisional, and responses are deliberately conservative to avoid false positives. As data accumulates, parameters are learned and thresholds are adjusted, but even then, there is a delay between detection and action. That delay is not a bug, it's a safety feature. Acting too early risks shutting down legitimate behavior. The problem is that attacks don't wait for defenses to stabilize. They occur during this initial time window while the system is still learning how to interpret what it sees. By the time the defense is confident enough to act, the interaction has already happened, and the information has already been extracted. Nothing here looks anomalous in isolation. The system is behaving exactly as designed, but the gap between uncertainty and enforcement creates a period where learning is one-sided. Defenders are gathering information to protect the system, while adversaries are gathering information to exploit it. The cold start problem ensures that the first moves always favor the side that can learn without committing to action. Here we see why systems that look rigorously specified on paper are often the easiest to manipulate in practice. Modeling starts by narrowing the world down to stable scenarios, because unstable ones are impossible to reason about formally. Inputs are constrained so they can be verified. Objectives are made explicit so success can be measured, and metrics are chosen because they behave predictably. That structure is exactly what allows proofs and automated reasoning to work. The problem is that the real world does not respect those boundaries. Attackers don't need to break the rules. They only need to operate at the edges of what the model already assumes. When scenarios are simplified, behavior outside that simplification becomes invisible. When inputs are verified against known values, novel combinations slip through. When objectives are clear, they can be optimized against. And when metrics are predictable, they can be satisfied without achieving real security. From the system's perspective, everything is behaving correctly. The checks pass, the goals are met, and the numbers look good. But the model is being satisfied, not the underlying security property. That's why assumption-driven systems fail quietly. They enforce rules that are internally consistent while leaving gaps where unmodeled behavior can accumulate. It's easy to build logic that works within its own assumptions. It's much harder to account for the edge cases, interactions, and adaptive strategies that live just outside the model. And that's exactly where real failures take shape. Up to this point, everything we've discussed has lived inside models, formal assumptions, clean abstractions, and proofs that operate within carefully defined boundaries. Those tools are necessary because without them we can't reason at all. But this is also where their authority ends. The real world does not respect model boundaries, and physical systems do not behave the way proofs assume they will. Once signals leave the page and enter hardware, cables, detectors, and noisy environments, entirely new behaviors emerge. Behaviors that were never part of the formal reasoning. In proofs, channels are idealized and adversaries are constrained by assumptions. In reality, channels are physical objects and adversaries interact with them continuously, adaptively, and indirectly. Nothing has to break. Nothing has to look wrong. Systems can remain compliant with every formal requirement while still leaking information through mechanisms the model never represented. This is the critical transition point, where correctness on paper diverges from security in practice. From here forward, we stop talking about what should happen in an idealized system and start examining what actually happens when those assumptions meet the real world, where mechanisms matter more than models, and where security fails quietly, not catastrophically. Here is an illustration of a category of real-world behavior that exists entirely outside the assumptions most security models make. Undersea fiber is a physical system. It spans thousands of kilometers, passes through amplifiers, junctions, and repeaters, and operates in an environment that was never designed for perfect isolation. From the perspective of an idealized protocol, the channel is abstract and well-defined. From the perspective of the real world, it is an object embedded in infrastructure, accessible at many points, and influenced by physics rather than formal constraints. What matters here is not how interception is performed, but that it can occur without interrupting service, without triggering alarms, and without violating the expectations the endpoints are checking. Signals continue to arrive on time, error rates remain within tolerance, and the system reports normal operation. This is a representative example of how mechanisms emerge below the level of the model, where information can be observed, shaped or extracted without ever breaking the system in a way the protocol recognizes. We're not going into the details yet. The purpose of this slide is simply to make one thing clear. Once security leaves the page and enters physical infrastructure, the guarantees of the model no longer define the full behavior of the system. Here, we see how detector behavior can look completely normal at every individual measurement, while still drifting in a meaningful way over time. Each detection event produces a count that sits comfortably within expected statistical noise, well below any alarm threshold, and from the system's point of view, nothing unusual is happening. The detectors are firing, the counts fluctuate, and the metrics remain inside their acceptable operating region. But when those events are accumulated across many interactions, a different pattern emerges. Small biases that are individually negligible begin to align, and correlations start to form that are invisible at the level of single measurements. The system's detection logic sees noise, because that is exactly what it is designed to see: short-term randomness bounded by thresholds. What it does not see is long-term structure. As time progresses, the aggregate behavior of the detectors drifts in a consistent direction, even though no single sample ever violates a rule. This is where adaptive strategies exploit real systems, not by forcing a detector to misbehave outright, but by shaping behavior so that learning occurs slowly, quietly, and persistently. The result is a system that appears stable at every moment, yet leaks information cumulatively, without ever triggering an alarm or signaling that anything is wrong. In security proofs, detectors are usually modeled as idealized components, independent, memoryless devices that respond only to the quantum state they receive and nothing else. In that model, a photon either triggers a clean detection event or it doesn't, and each event is statistically independent of the last. That assumption makes analysis possible, but it quietly removes the physical reality of how detectors actually behave. Real photodetectors are physical systems with thresholds, nonlinear responses, recovery times, temperature dependence, and history. Their outputs are shaped not just by the incoming quantum signal, but by noise, drift, saturation effects, and correlations that emerge over time. From the system's point of view, everything may still look normal. Counts fluctuate within expected bounds, error rates stay below alarm thresholds, and nothing appears obviously wrong. But at the physical level, subtle structure is forming. Small biases accumulate. Correlations emerge between events that are assumed independent, and behavior that is invisible in single measurements becomes detectable when aggregated. This is where the gap between assumed behavior and actual detector physics matters. An adversary doesn't need to violate the model outright. They only need to interact with the physical system as it really exists. By shaping inputs to stay below detection thresholds while exploiting detector nonlinearities, they can extract information without triggering alarms. The proof remains satisfied, but the security property it was meant to guarantee no longer holds in practice. This is not a failure of quantum mechanics. It's a failure of assuming that physical devices behave like abstract objects. And this mismatch between idealized assumptions and real detector physics is one of the core reasons quantum security systems fail quietly, not catastrophically. To close this out, the core lesson is simple and unavoidable. Security proofs are mathematically sound, but they are only guarantees within the assumptions they make. Real quantum systems are not abstract objects. They are physical, noisy, stateful devices operating in an uncontrolled environment. Attackers don't need to break protocols or violate proofs. They exploit hardware behavior that the model never accounts for. Detectors, sources, and channels leak information below detection thresholds long before alarms are triggered. Passing checks and meeting error bounds does not mean a system is secure. It only means the model has been satisfied. Real-world quantum security is not something you prove once. It is something you must continuously measure, validate, and adapt over time. Security is not a state. It's a process. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit SpecterAI.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.